And hello everyone. So I'm Xiaohong Chen from PySquared. It's a great pleasure to be here today and share with you our latest technology called proof of proof. It is an approach to universal verifiable computing for all programming languages. Before I start, I'd like to talk a bit about us. We are a new startup established at the beginning of the year. Our company name PySquared stands for proof of proof. So pi means proofs, and we are dealing with two types of proofs. So zk proofs of mathematical proof. So that's why we name our company PySquared. Our founder and CEO is Grigori Russell. So he's also a professor at UC, and he's also the inventor of K and matching logic, which are the two core technologies that enable what we do here. I'm the CTO and the main force behind the matching logic and zk. I also got my PhD from UC. Patrick McKay is our CEO, and Shyam Vishwanath is our head of BD and strategy. We are backed by our global investors, with Antchain being the lead, and our angels. So in this talk, I'd like to give you a very high-level overview of what proof of proof is. It is one of the most fundamental and game-changing technologies that are being developed here. So it is an approach to universal verifiable computing. So it takes as input a programming language, a program written in a language, and the entire execution environment, such as input data, environment variables, I/O, and so on. And eventually, on the very right-hand side, it generates a zk proof as the output. So this zk proof shows that the program has been executed correctly in the given execution environment. What's interesting here is that proof of proof is universal. So it's not specific to any particular programming language or virtual machine or instruction set architecture. Instead, any programming language, virtual machine, or ISA can be passed to proof of proof as an input, as a parameter to facilitate the generation of zk proofs. And in the following, I'm going to present you how proof of proof works step by step. So the first step, step one of proof of proof, is to take any programming language as input and generate an interpreter. So at proof of proof, a programming language L is given a formal semantics, so which is a rigorous mathematical definition that specifies the behaviors of any programs in that language. And the core technology here is the K framework and formal semantics. From the formal semantics of any programming language or virtual machine or ISA, K can automatically generate an interpreter based on the semantics. And then in step two, we use the automatically generated interpreter to execute programs written in the language. Given a program and its execution environment, the interpreter can execute the programs using the formal semantics and obtain what we call proof hints. The proof hints include information such as the initial and final states, as well as the entire execution trace. And this information will be used to generate the final correctness proof. And the core technologies here are, again, the K framework and its high-performance pattern matching algorithms. The algorithms aim at making the interpreter, which is automatically generated by K, to have a competitive performance with handwritten, handcrafted interpreters. Once we obtain the proof hints of a given program, we carry out step three of proof of proof and pass the hints to a mathematical proof generator. The result is going to be a mathematical proof that shows the program has been executed correctly. The core technologies here are K and matching logic. So matching logic is the logical foundation of K. Any properties about program computation can be stated and proved in matching logic and encoded as a matching logic or mathematical proof. And at this point, we already established universal verifiable computing, where the mathematical proofs are the correctness certificates. But mathematical proofs are known to be usually very large, so we're going to combine them with zero-knowledge technology to reduce the sizes of the final certificates. And that's the last step, step four of proof of proof, is to use a mathematical proof checker to check the mathematical proofs. Furthermore, we implement the checker inside a zkVM to obtain a zk proof. So the zk proof shows that there exists a valid mathematical proof for the given execution trace of the given program. In other words, the final zk proof hides the large mathematical proof as a witness and only argues for its existence. And we use zk technology to do massive proof compression here. And the core technologies are matching logic and all the existing zkVMs on the market. To sum up, proof of proof is an approach to verifiable computing for all programming languages, virtual machines, and instruction set architecture. It takes as input a programming language, a program, and the entire execution environment, and outputs a zk proof that shows that the program has been executed correctly. As we can see from this diagram, proof of proof has two phases. So in the first phase, it generates a mathematical proof that also shows the program has been executed correctly, but it's very large. So in the second phase, we use a mathematical proof checker implemented in a zkVM to hide the mathematical proof and obtain the final zk proof, which is much smaller and succinct. There are quite a few unique advantages of proof of proof. Firstly, it doesn't require any compilers or transpilers or interpreters of the target programming language. If we really have to say here, proof of proof compiles any programs in any programming languages into mathematics and logic. So it gives us the best possible universality ever, and it avoids compiler, transpiler, interpreter bugs. And it enables mathematical level, what we call out-of-the-box optimizations, such as using formal verification properties to skip loops. And by doing so, we reduce arbitrary computation of any programs in any programming languages into mathematical proof checking, which is much simpler. And it's also an embarrassingly parallel problem. And there are many other advantages and benefits that are well known in the area of programming languages and formal semantics, but are not so well known in the community of VC. So proof of proof is trying to introduce all these research and engineering results that exist in the area of formal methods and programming languages to VC, so we can take the best in both worlds. Proof of proof is also compatible with any zkVM. We can implement the same mathematical proof checker in RISC-0, zkWatson, Kailo, SP1, and many others. And we are collaborating with these zkVMs to obtain the best performance. To sum up, proof of proof is a divide and conquer approach to universal VC. In the following, I'll elaborate on a few core technologies of proof of proof. The first core technology is the K framework. The motivation of K is the fragmentation in the state-of-the-art programming language design and implementation. So for example, we have many languages nowadays, and for each language, we need various tools, interpreters, compilers, formal analysis tools such as model checkers and verifiers and so on. And what we do here is for each language, we design and implement each tool separately. So we end up with having an interpreter for C, a compiler for C, and so on and so forth. And we do the same thing over and over again for all languages. So if we have L languages and T tools, we end up with L times T systems that need to be designed, developed, and maintained. At the very least, it's not economic and results in a significant waste of talent and effort and duplication work and so on. So the K framework proposes a different vision. In this vision, the K vision, programming language design should be separated from tool implementation. On one hand, we can formally define the formal semantics of any programming languages, virtual machines, ISAs in K without worrying about implementing tools. On the other hand, K offers language parametric implementations of these tools, such as an interpreter, compiler, a symbolic executor, model checker, verifier. These tools are language parametric, or they're actually tool generators in the sense that they can be instantiated by any given programming language. So in this K vision, every programming language has a formal semantics, and every tool has a generic implementation in K, which can be instantiated by a formal semantics. So if we have L languages and T tools, we only need to maintain L plus T systems instead of L times T. And for users and language designers, K allows fast prototyping of your ecosystem because you can simply plug and play your programming language in K and automatically obtain all the tools for your language. The second core technology is matching logic. So matching logic is the mathematical and logical foundation of K. Every formal semantics defined in K represents a set of mathematical actions written in matching logic. So for example, the formal semantics of EVM, the Ethereum virtual machine, in K, represents a set of mathematical actions called gamma EVM, and these actions specify the behaviors of any EVM program's code using rigorous mathematical definitions and notations. And such that any program execution trace is associated with a corresponding mathematical obligation which can be proved. For example, if Alice transfers one token to Bob, the corresponding state change on EVM will be encoded by a mathematical obligation of the form phi init arrow phi final, where phi init and phi final represent the initial and final EVM states before and after the transaction. And thanks to matching logic, we reduce the problem of finding the VC proof for the EVM transaction into finding a mathematical proof for the set mathematical obligation using the mathematical axioms. So we reduce the problem of universal VC into a much simpler and specialized problem, which is looking for a mathematical proof. And matching logic is a very simple logic. What I show here is the entire proof system of matching logic. It has only 15 proof rules, and yet years of research shows that this simple proof system is sufficient for proving any execution traces of any programs in any programming languages. In other words, these 15 rules are all we need for universal VC. And at the very same time, these 15 proof rules are very simple to check by a program called the mathematical proof checker. And since each mathematical step can be checked entirely in parallel to other steps, the checker is easily parallelizable. And what we obtain from matching logic is a simple yet universal mathematical proof checker. And given a mathematical proof, it either accepts or rejects it. And our final core technology is to implement a set mathematical checker inside a zkVM. By doing so, we obtain much smaller proofs, the zk proofs. The mathematical proof shows that a given execution trace of a program is correct, while the zk proof takes the mathematical proof as private input and hides it and generates an argument that shows that there exists a mathematical proof that shows the statement is correct. So from a mathematical point of view, these two proofs prove different arguments, but from a user's point of view, both are sufficient to serve as VC certificates. And zk proofs are preferred, of course, for their sublinear or even constant proof sizes. To sum up, pi-squared proof of proof is an approach to universal verifiable computing for all programming languages. It means zk proof of mathematical proof, so divide and conquer, and it gives us best universality ever. It avoids compilers, transpilers, interpreters bugs, and it's compatible with any zkVMs. And before I conclude my talk, I'd like to share some information. So firstly, we're hiring. So if you're interested in what we do, please take a look at open positions on our career page. And we'll raise soon, hopefully within this year. So, and if you're interested, feel free to reach out to us. And here concludes my presentation. Thank you all for listening.